So we talked about atomic structure, protons, neutrons, electrons. Electrons are our primary focus for organic chemistry. Okay? Where the electrons are, what electrons are going to interact, how they interact. And so we've got energy diagrams, Gen Chem. We move up in energy, we end up with a new orbital type, okay, with different orbital orientations. And we can go through and populate those with all of our electrons, okay, which I believe this is straight from a Gen Chem lecture I gave, so nothing exciting there. Our s orbitals were spheres. P orbitals were the lobes, right? All that makes sense? Okay. How many orientations are there for a sphere? One, which means we only get one s orbital for an individual energy level. But for a p orbital with the dumbbell, can you tell if it's been rotated? Yeah. So there are three primary orientations for a p orbital, hence the three types of p orbitals. So we end up with more p orbitals than we end up with s for an individual energy level. All still straightforward? I'm going to say yes. So this should look pretty familiar because you will see this on every test. Okay? It also should look familiar because it's similar to what's on the wall. What's different about it?
It's missing the transition.
It's missing the transition elements. It's missing the other ones, the radioactive ones, the lanthanides and actinides. Okay? It's also missing a couple rows through the standard part of the periodic table. Okay? So why is organic chemistry cool? Well, we look at that and we say, or look at the big periodic table and say there's too many elements on that. I don't want to look at them. So I'm going to get rid of them. I'm not going to worry about them. Okay? So we simplify it down. Okay? And we say, well, I only have 10 fingers, so there's still too many. So I'm going to get rid of some more. And we look at organic chemistry, that's pretty much what we're looking at. We will branch out every so often into, say, sulfur or phosphorus. Sometimes we look at the transition elements. But for the most part, that's our home. That's it. Okay? So what you need to know for those elements would be, what do you think?
Atomic number?
Actually, the atomic number won't even become important, which is also interesting because notice the atomic number isn't actually on this periodic table. Mass could be useful. It really shouldn't be included on this table either.
Electron configuration.
Electron configuration, sort of. What about the electron configuration? Valence electrons. How many valence electrons do we find for each of these elements? So if you have that information quickly available, instead of having to look at the periodic table, oh, I know carbon has 4 valence electrons. I don't have to worry about finding it on the periodic table or anything else. I can just work from that. Okay? So knowing its valence electrons can become important. What else might be important? What are the valence electrons going to be used to do? Bonds. So maybe a useful thing on here would be to know, how about how many bonds? How many bonds should that element have? Okay. What did they make you memorize in Gen Chem as an extra thing on here? I know, there's tons of things, right?
Size.
We could look at size. That's actually a good one. I didn't even think of that. Size is a good trend. That's actually a good one, though. I was looking for a bad one.
Electronegativity.
Electronegativity is like the most important one to remember. So the guesses are good. They're just not the right, wrong guesses I wanted.
Color.
How many of you memorize the color of any element? Charge. You might have memorized charge. Charge is a bad thing to memorize. Ignore that. Okay? We won't worry about that as far as the memorization goes. We'll have to worry about calculating it, okay? But that's not going to be something given to us off the periodic table. Okay? Phase. Might also memorize that. Not useful. Okay? Those are going to be the big ones that we need to nail down. Okay, so where can we get that information? I guess I could have color-coded this. So valence electrons. Anybody want to give me some information on where you find the valence electrons? So look at the group number. Okay, conveniently none of the group numbers are listed up there. So there's one valence electron. How about for magnesium? This is getting harder. Boron? Remember, organic chemists can't count beyond 10. So cool. Where's that? We now have our valence electrons. How about size? Because bonds is going to be tricky. What can you tell me about size? This is actually going to be an important one. Down and left. So everybody has this weird memorization thing to figure it out, and I can never remember it. So as we go down a column, what happens? It gets bigger. So size gets bigger as we go down. So we'll say big down here. Actually, let's just say bigger. Okay, so that's in our column. What about left to right?
Bigger is small.
Nope. Left to right. Decreases, okay, which is counterintuitive because we're adding more electrons just like we do down the column, but it gets smaller. Okay? That's what Gen Chem told you, and it is officially true. Organic chemists simplify. How much does it change within a row? Barely. Which means, is there a size difference across the row?
Slightly.
Not that matters. It's not applicable across the row. When we're comparing carbon to nitrogen, their size is the same. When we compare nitrogen to fluorine, their size is the same. Okay? True, no. Close enough, yes. Okay? So we've got size on here. We've got valence electrons. How about electronegativity? Fluorine is our most electronegative. What's our symbol for electronegativity? Because I don't want to write that word again.
En.
What's that?
En.
Oh, that's actually not a bad one. I have heard En. The other one I've seen is Chi. Okay. I think that's Chi. Is that Chi?
Yeah, it's good.
Okay. And lowest electronegativity. Okay, in the opposite corner. What are the three most electronegative elements? Fluorine, oxygen, and nitrogen. Is it going to be important to know those three as the most electronegative? Yes, because they contribute to hydrogen bonding. Not bonds, hydrogen bonding, okay, which is irritating. It's not a bond. Okay. How about we get to the last one, the number of bonds? How many bonds can hydrogen have? How many bonds can sodium have? 1, okay. So that column was 1. Boron, or sorry, magnesium. Boron. Carbon. Nitrogen. Oxygen. Fluorine. 1. Okay. These we might say are the maximal amount of bonds. Okay. So let's take a look at an example, because you know examples are always useful. Let's look at, say, CH4. How many bonds does the carbon have? 4. Well, that matched our rule. Okay. What do you think I'm going to draw now? How about ammonium? How many bonds does the nitrogen have? 4, but our list said 3. What's wrong? Has to do with the charge. Okay? So when we're identifying the bonds, we're identifying the bonds in their neutral state. And even that becomes kind of questionable. But we're aiming for our neutral state primarily for each of those. Those are useful things to remember, because then when we go through to draw out Lewis structures, we don't have to go through a whole bunch of fancy rules. We already have the pattern down. I know that when I draw a carbon, it has to have 4 bonds. I'm going to draw those 4 bonds. Okay? If I'm going to vary outside of that by adding a charge, I know I'm going to vary outside because of doing those bond characteristics and how things shift from that. Okay? So having that information memorized can help me. Does that make sense? Okay. We could bring in orbitals. Want to look at orbitals yet? Still kind of early. It's not even noon. Okay, we'll come back to orbitals. Functional groups. Oof. Big old mess of functional groups jump out of this. Okay, and this is kind of a bizarre place to throw in the functional groups, because do we know why we have bonds or any of that nature yet? Not really. We didn't talk about it, at least in this class. And yet we're now throwing a bunch of functional groups at you. And we're throwing them at you early because you need to be able to recognize these functional groups. When you go from first semester through second semester, you will see all of these functional groups and more. And what you are expected to do with those structures is, when you see them, know how they react. Know what they're going to interact with. What is likely to happen, what is likely not to happen. And believe it or not, at the end of second semester, you will be able to do that. It's kind of neat. Because that looks really scary right now. How much of those are you going to be responsible for this semester?
Hopefully not.
There's some optimism. Okay. We'll be looking primarily at our alkanes, the alkyl halides, the alkenes. We'll see a little bit of the alkynes, but not quite as much, so just half a star there. Alcohols, probably a half star. Ethers, probably not really. Aromatics, not really. And then pretty much everything on the right is second semester. So that's not too bad. Less than half of them we're really keeping our attention on. Will we see the other functional groups pop up? Yes, but in slightly different formats. Okay, we'll look and see how they interact outside of a reaction. Okay, maybe they're contributing to it by helping the reaction along, okay, or they're dissolving something. So you need to be able to look at and see very quickly, that's an alkene. Okay? That is an aromatic structure, which should really be changed to benzene. But, okay? So if you haven't done so already, start working on devoting what the functional groups are to their structures. How do we get to functional groups, though? Okay, we're starting with atoms. How do we get to compounds? So we've got a drawing of 2 different atoms here. What atoms would those be? Helium. How do you know they're helium? 2 protons. Okay, so looking at the drawing. Okay, so what we're doing is taking any 2 atoms and we bring them near each other and we say, does something happen? Okay, in the case of helium, does something happen? Anybody know? Okay. We get a minor attractive force, but we don't make any new bonds. Okay. And that's because when we think of helium, helium is in which column? The last one, known as the noble gases, because they don't react. Okay. Helium doesn't react. So when we bring them to each other, we might not expect an interaction there. But what if we change the atom? Okay. Could we see an interaction then? Yeah. So what are the things that are going to contribute to that interaction? Any guesses? Angle of impact. Ouch. Absolutely valid and true. We really don't want to look at that. We just kind of assume, yeah, the angle of impact was good enough and it worked. Okay. What else is going to be important?
The empty orbitals.
Empty orbitals. So I remove all of the electrons. All the orbitals are empty. Do I get an interaction? No. Because to have a good interaction, what do I need? Electrons. I need some empty and some not. Okay, so it's the balance of electrons being present and electrons not being present that are contributing to our bonding patterns. And we're seeing how those electrons interact in those systems. which electrons might we predict to be the most important for generating this interaction? The valence. Oh, that's why we said we should know the valence electrons. Okay? We need that information because those are going to be the important ones for our interaction. Okay? So, when we mix these two, we get two potential options. Option A, we get a really strong interaction. We get such a strong interaction, we go, I'm going to call that strong interaction, because strong interaction, way too many letters. Remember, 10's our cap. And I think strong attraction is more than 10. We're going to call it a new name, bond. Sounds fun. Okay. What happens if we don't get a bond? Well, don't get a bond is too long. We could call it not bond. Very creative. Okay. I like where your mind's going with this. Okay. So we now want to look at possible variations. Are there going to be possible variations? Would I expect all bonds to be equal? Okay. Why not? Why are we seeing ionic bonds, covalent bonds, polar covalent bonds? Why is there differentiation? What do you mean? Yes, there's a word associated for that, sharing electrons.
Sharing 50-50 or sharing not through.
Why would an atom, do we have a system organized to say that atom is going to share electrons versus that atom is not going to share?
Yes.
Electronegativity. Oh, that's right. That's one of the other things we said we needed to be familiar with. Because what we're looking at for that sharing comparison is our electronegativity. Do they share? Do they not share? Okay? So the types of intramolecular attractions, also known as bonds, within our structure, you've already identified. Ionic. How do you know it's an ionic bond? Metal and a nonmetal. So anytime I have a metal and a nonmetal, I have an ionic bond. Okay, no other cases? Just metal and nonmetal? Anyone want to hedge your bets and say, no, there's exceptions? Okay, you're running with it. What type of bond? Where's the metal? Okay. So our ionic bond rule of thumb is metal and nonmetal. Really, what are we looking for? Ions. Do we have ions? What is ammonium? It's ammonium ion. Okay? So the rule of thumb is useful, but realize there are exceptions to that. And I will write these rules of thumb down in a second. Okay? Polar covalent. Okay? Anybody that's had me before can't answer this. What is our polar covalent bond? How do we know I have a polar covalent bond?
There's one that's extremely electronegative. It takes most of the electrons, so the other one's positive.
So that's a polar covalent bond? Sodium is a metal, fluoride is nonmetal. You just said the extremes, I just picked the extremes. So it doesn't quite work. So what you are trying to work with on that is pushing for an extreme definition, getting back to quantification. What are the electronegativities? And strictly speaking, yes, you are correct. Okay? But you have to be very careful in that assessment. The electronegativities for an ionic bond, the difference in electronegativity between the atoms has to be greater than 1.7. To be a nonpolar covalent bond, the difference in electronegativity has to be less than 0.5. To be nonpolar covalent, what do we have to be? Somewhere in between. I think I'm writing that in the wrong spot. Okay, how many of you are going to spend some time memorizing your electronegativities now? Don't do that. Don't do that. That sucks. You don't want to do that. Okay? This is why Muhammad did not suggest right out of the gates difference in electronegativity being greater than 1.7. What did you suggest, Muhammad, for an ionic bond? I'm writing it as you think about what you said. Metal and a nonmetal. Okay. We ran into an issue earlier. What was your name? Sorry.
Elizabeth.
Elizabeth. Okay. With Elizabeth's definition, because it was too broad and it covered ionic, okay, how can she drop in a definition that matches that? Well, that means we'd need to know the exact electronegativities, and we said that's an awful idea. We don't want to do that. Okay? So let's skip polar covalent, because that is a hard one to work with. Let's move to our nonpolar covalent. Notice the nonpolar is in quotes. Why? I think I'm going to invent a term for this. And that term is going to be the 10-finger term. Nonpolar covalent has more than 10 letters, and I can't keep track of it, so I just call it covalent. Polar covalent, sorry, I got to use my toes. Okay? But nonpolar covalent, if I can avoid it, I'm just going to leave the polar covalent as its own little exception. So when I say covalent, I'm saying nonpolar covalent. How do I know I have a nonpolar covalent bond? Okay. Electronegativity was a possibility, but that's one we don't want to memorize. We want a rule of thumb. What's that? Two nonmetals. Unfortunately, polar covalent matches that exact definition. So we need something more broad than, or less broad than just two nonmetals.
Carbon and hydrogen.
We did jump for like the exception one. Carbon to hydrogen is defined as a nonpolar covalent bond. Okay. As you might guess, there are two rules that we need to memorize for our nonpolar covalent bonds. Because I started carbon to hydrogen as rule number 2. Yeah. You don't have to laugh. It's okay. 1, you're not supposed to laugh at the don't have to laugh. Rule number 1, our difference in electronegativity must be less than 0.5. When am I going to get a difference in electronegativity that is small? Same atom to the same atom. Or just same to same. Keep it simple. That shows up somewhere else, actually. So, back to the hard one, polar covalent. How do we know we have a polar covalent bond? Again, my students can't answer.
Everything else.
Takes all the fun out of it.
Wait, back up.
Everything else. Everything else is defined as polar covalent. Is that perfect? No. Just like ionic wasn't perfect. Okay? But it gets us darn close. So I need to memorize two definitions. The definition for nonpolar covalent and the definition for ionic. If my structure doesn't match one of those definitions, it is now polar covalent. And I've classified the bond type. Okay? Is knowing the bond type going to be useful? Yes. That's what explains how things react. That's what explains why things dissolve and don't dissolve. Okay? Which you were tested on in 151 and in 130. Because I know that because nobody knows how to answer those questions from those courses. Because they never get taught. But that's okay. Okay? So, let's move it to the next part. Now that we know what our bond classifications are, let's actually make a structure with bonds. So, work with the people around you, 3 or 4. If you want to work by yourself, that's fine too. I'm okay with that. Provide the Lewis structure for the complex ion sulfate, SO4 minus 2. The more important part of this is going to be writing out the rules for how you got to that structure. That's what we want to see. Okay? Once you think you've got it, get it up on the boards. Why any of them? They're all the same. So let's pick upper right. It's supposed to be red. Where do I want to move those electrons? Well, so far I only said I could do bond to atom or atom to bond, so I only have one choice. I can only go bond to atom. Which atom do I want to move them to? Top or bottom? I'll agree with you for the sake of time. Does it matter? The answer is no. We would end up building a negative charge there. Why would we have a negative charge at that position now? I moved electrons to that atom. I gave it an extra electron. It is now negatively charged. If you want to verify that, calculate your formal charge. You will see that to be true. What happened to the other carbon? It lost an electron. So it would become positive. You can verify that with your formal charge. You'll get positive. Okay, now what happens? Well, that looks like an ugly structure, so let's try and move some more electrons. We can move those electrons to here. But now what happens? I've exceeded the octet there, so I can move those electrons from a bond to an atom.
The same here.
It's a different, harder question than is possible to answer. It is indistinguishable. We can't tell the difference. I'm going to stop drawing the hydrogens for a second here. And we'd end up there. What if, at the very beginning, I just said this? Instead of going bond to atom in my very first step, what did I do? Bond to bond. I'm allowed to do that as long as it is the immediately next bond, because those electrons are close enough that they can jump, because they're passing through that atom. That is a valid maneuver. If you were asked to draw Lewis structures, the middle one is rarely shown. We almost always would show something more along these lines. Okay? If you continue to propagate this out, what we end up finding is that we can draw this structure like so. What is special now about this structure? It is not charged, yet the double bonds have all appeared to have moved locations. We've drawn a new structure without introducing charge. We've created an entirely brand new, awesomely stable molecule. Way beyond time. Well, way beyond. 3 minutes. We'll have lab anyway. Okay? With that,